In this video we will implement the very abstract KD tree which can contain any type of an element, not just a pair or triple, it can be any element. And also we will build a balanced KD tree and implement the range search function. By the way, you can read about what I want to do is, this is some related question which I create on Stack Overflow. I put this link here, and now let's go to actually our type class. So I will call this type class kDimension, and this kDimensional class must be implemented on some containers, okay? So I will mark these containers as C. So this is actually our container, our type on which we want to implement the KD tree. And we have some other type. I will call this type Q. This means that this is a query type. So we have our k-dimensional tree and we have the query. And for each type of this container, k-dimensional container, we will have some query type. Okay. And we can see now that our query type is uniquely determined by our container. So this is functional dependencies. I use it here. Okay. And now let's do some implementation of the methods. Sorry, let's write the function, set of function which present our type class, KD type class. So the first function, I will call this function dimensions. And this function will take this container and return the integer. So this is how many dimensions have this container. What I mean dimensions? What if they have, for example, the pair of values, and they want to construct a KD tree. In this case, for pair, where is it two dimension, the first element and the second. If they have triple, for example, they have three elements, and so where is the three dimensions. So I need this information when I will implement the building of the KD tree. The next function which I want to implement is the compare kth element. So this function will take the number of the field in our container. So for example, if we provide 1 and we have pair, this means that they want to compare the first elements of the pair. And we have the second container, first container and second container, and then we compare them. Of course, we return the ordering type class. Okay. Well, the next function is I will call it range check. This function also take the field index in or the field number in our container. It's take our container and it's take the query. So, and using this query, we want to answer the question. What is the relation of this field and query? And what I mean by relation? So here I mean that we have point interval relation. So let's write this. Point interval relation. Okay, and to represent this relation, I want to create the data type, and in which positions can be the point with the interval. So the point can be inside interval, it can be from the left of the interval, and from the right of the interval. So we have three cases here, and I will represent them with my new data type: inside, left, and right. Okay. And let's derive show and equality instances for this simple type. Okay, now we can compare them and print them. And here we, in this range check function, we check the point interval relation. So we have the interval inside this query. And we have the point as a field represented by this integer in our container, inside our container. Okay. And now let's implement the simple function, simple helper function, which will help us little bit. It will need to us a little bit later. I will need this function a little bit later. Sorry for my English. So we have some function pause, which takes some point A and takes some interval from and to. It has ordering type. Sorry. So here I present I do the implementation, but here I need to fix its type signature. It has the ordering type, it has the point itself, then it has the left part, leftmost point of the interval, and the rightmost point of the interval, and it returns to us our point interval relation. How we implement this function? We must to check three cases. If our A is less than left point of the interval, then V from the left. If our A is greater than right point of the interval, then V from the right, and otherwise we inside. Okay, I think like this. Or we can write this case explicitly. In this case, we must have this relation. We must be greater or equal than from, and at the same time we must be less or equal than to. Okay. And now when we have these functions, abstract functions of the type class, we can actually implement the inside function. What is the inside function? Inside function is take container, some container, KD container, k-dimensional container, and some query for this container, and it produces to us the boolean. So actually this function is answer the question, is our container inside our query or not? Okay. And we can do the implementation now. because we have all these three abstract functions, and using them we can do the implementation of this function. So how to do this? To say that our container, KD container inside our query, we must check that all the fields from zero to dimensions inside our corresponding query intervals, and each interval we can check this function. Okay. What I mean? This means that I must take all my dimensions, and we can do this by using this function. We can provide for our container the dimensions and construct a list from 0 to dimensions -1. So I will index them from the 0. Okay, then we have these dimensions. What they need to do? They must use so actually they need to check that all dimensions are inside our query. So we can use all functions. It takes some foldable T. This is our list, and it takes also the predicate. So I can use for predicate lambda function here, which gives which takes index, and so this index will be is extracted from this list. They take this index, and using our rcheck function for this index, for this given index on our container and with our query, we must check that our if point inside this interval. So we write this as this equality. Okay. So actually I have now this abstract KD container, and we have all to implement our KD tree. Okay, but let's start from the some concrete containers. So the simplest container that we can use for this type class is a simple pair. Actually, I must implement this type class to my pair and the query for this pair. So at first, let's do the type for our query for this pair. So we have pair, and this have some query which can be used to query some data from KD of this pair, KD tree of this pair. How we implement this pair query? So it take A and B, and actually it had two intervals for the first element of our pair and for the second element of our pair, and maybe we can not have these intervals. So what if you want to skip one interval? What if you want to find only by one interval? Okay, and I will provide type for this thing. So this means to me that I can use a maybe type, and the first element here is a pair of A and A, and also there is a second type with a maybe pair from B to B. So we have pair of pairs, and this is our actually our pair query type. Okay, and let's derive show for it. Now, for example, I can create this pair query like this with my PQ constructor, and I want to, for example, provide just 1, 2, and just 3, 4, for example. This means that I want to have the interval by the first field from 1 to 2, and by the second field from 3 to 4. Okay. And now let's implement the instance for my KD class, for my pair query, and for my pair. So I will do this in a moment to make this video a little bit shorter. So you can see this implementation here. They must have the ordering A, ordering B, and this pair A and B, and some pair query AB. And for these two types, they can implement the k-dimensional type class. We can say that they have 2 dimensions because pair have 2 dimensions, and they can very easy implement the compare the first element function. So to implement the first element, they need to unpattern match our pairs and compare first elements of these pairs. And also for the second element, they need to compare the second elements of these pairs. And if they have, otherwise they have some n which exceed our dimensions, then they will throw the error. Okay, and also we need to provide the check function. And this will be the last third function of our KD type class. So we have here simplest cases. We can have the pair, if we have the pair, and we have pair query with which contain the first interval, then we unpattern match it here and use our position function to determine the relation of the pointer and the interval. And this is and also for the second element, and also we must catch the cases then they have no inquiry information about some interval. If this is nothing, then they say that all the points can inside our interval. So if they have information about interval, they assume that that any points satisfy to this query. Okay. Now let's try to compile this a little bit. Let's try to compile this. I can't compile a little bit. I can compile all. Okay, errors. Okay, I do some typing error here. Maybe. Okay, we load this. So let's try to, for example, we can simply use our dimensions function with this pair. Okay, you can see that it has 2 dimensions. Also, we can use compare if function to compare 2 containers. For example, if we have 1, 2 and 2, 3, and we want to compare the first element. you can see that 1 is less than 2, and we have this information here. Also, I can compare the second element. Because I index from 0, I want to can compare the first. It is 1 is less than 2, and I can compare the second. The second has index 1, and it also less, but if I change it, you can see that we have the equal. Okay, and I can use the range check. What if I want to range check, for example, this first element and this 1, 2 container, and we have query, which I already defined here. So with query have from 1 to 2 the first interval, and second from 3 to 4. Okay, in this way we can compare, check that our first point, this is actually 1 inside our PQ. Okay, and you can see that it is inside because 1 is equal, 1 is inside this range. Also, I can check for 2, and you can see that for the second point of our pair, this is 2, it lies from the left of this interval. Okay. And also I can use inside function in the same way. Inside function, if I have some container from container 1 and 2 and have some query PQ, this tells me that it is not inside because this 2 is not inside this interval. But what if I put a 3 here, and 3 will go to this interval, and if I run this, we can say true because because we inside our actually box, two-dimensional space. So we inside this query. Okay, but let's provide some more example. What if I have some more real-life example? For example, some data structure which represents a man, which have a name, age, and height, and I want to find the man with which age inside some interval, and each age or age, and also with height inside also some interval. So I need to provide the two data types here, one for man description and one for man query description, and I will write it in a moment. And wait a moment, and I will do this. So we have here our man, which actually is 3 fields. The name is a string, the age is an int, and the height is an int. I think I can format it a little bit in a nice way, like this, more readable. Also, I have the man query. Actually, this is 3 intervals. We have ordering on string, and that's why I can provide here the pair of the strings from 2. And also we can provide the interval for our age, interval age. This is 2 integers, and height. This is 2 height. Okay. And for example, we can construct such a query MQ and such a man1 and man2, And now let's implement the type class, our type class, KD type class for this container. Actually, man is a container. And let's do this. So I do this implementation. It's very simple. We have 3 dimensions here: the name, the age, and the height, and we provide the corresponding comparing in every dimension. Also, we provide the checking for each intervals, and also I provide nothing here if I don't want to use some of the intervals. And that's all. We can use our searching with our interface, KD interface. So, for example, I can run I can check inside my man1 inside the man query. So I need to reload and check. And you can see that man1 inside my query, because it's age inside this range, it's height inside this range, and its name inside this range. So, but what with the man2? The man2 is not, because his name outside of the first range. So I think this is a very nice, pretty interface for dealing with k-dimensional containers. And it can be used to implement the KD tree. And let's start our KD tree implementation with insertion function. Okay, it will just insert the elements into our KD tree. Okay. So here I do this implementation for KD tree. What we have here? We have binary tree. Binary tree represented by this data type. So each either the empty node, either the node A, the left and right subbranch. Okay. And what we do here? We have binary tree of this type A, the element A which we want to insert, and we produce a new binary tree after the insertion. And of course, we have this A type. It must be instance of KD. Okay. Okay, and how we do the insertion? So we use some helper function here. We provide some initial tree, initial element to our function, and also we provide the start index of our field. So we start from the first field. This is index by 0. And here we have some cases. If we have the empty tree. Okay. If we have empty tree, we just create a node with our inserted element with 2 left and right subtrees. But if we have not empty tree, if we have a tree with some element and left and right some branches, and our inserted element, and k is the index of our dimension. In this case, we work in this k dimension. So according to the KD tree definition, we compare our inserted element with the node A. by this dimension. And if it's less, then we must insert our element to the right. Okay. So, and if it equal, we also insert it to the right, and we construct our node again, but use our helper function again with recursion. And in the left case, we go to the left. Okay. But also here we increase our level of the dimension by 1. So we define it like this. So on every step we increase it by 1, but with this modulo they stay in our range of dimensions. Now I can implement such a function from list, which will take some list of my elements and will use fold L function to insert, to do the insertion. Of course, we start from empty tree and using our list. So this function which actually do construct a KD tree, but this will be not balanced KD tree. Okay, let's try to run this function. So I will use from list and will provide some pairs. For example, 1, 2, 2, 2, and 3, 3. So I need to let's name this function like this. So you can see we have this tree, and let's print it. So as you can see, it is not balanced, but here we have from the right the element which have 2, as a first pair element, as the first element of the pair, and this is greater than 1, and that's why it is on the right. And here we have which increase our dimension, and we have 3. It's also greater than 2, and that's why it from the right. But if I change it to the 1, you can see it goes to the left. Okay. Now let's implement function which will construct a balanced tree. I will do this. So I do this implementation. This is build balanced KD tree function. How it works? Of course, we use the helper here. We built our balanced KD tree from a list. If they have empty list, they have empty tree. Otherwise, what if they have some list and they have some dimension k? How we can construct the balanced tree? We can break our list into 2 parts. The first part is less than our. So at first we sort our list by kth component, kth field. We use this function sort by, which takes. Let's look at its type signature. This function takes some ordering function and the list of elements. And for ordering function, we use our compare k function with the k dimension. So we here work in some dimension. This sort by this dimension. and have the sorted list. When they take the median of this sorted list and split this list into two parts, less than median and greater than median. Actually, I can a little bit simplify this code. I think I will do this a little bit later. So, and the recursion, they go deep and deep to the left and to the right, building this tree. Okay, let's check that this works. For example, I have a list of some pairs. I think we can run it. And what if I print this tree? You can see this is a balanced tree, so I can add some more elements, and for example 1 7 1 8 2 7, and it will be always balanced tree. As you can see here, we have 5, it's from the right because it's greater than 2, and here we have 2, but why we have 2 here? I understand why I have this 2 here, because building a balanced tree in this way, we have the problems, then we have the duplicates elements on some dimensions. So I have this 2 here, and then I sort this list, these duplicates. So I must somehow handle them, and to handle them I need to modify logic. I think it will be more complicated, but let's assume that case k dimension keys are unique. Okay, I need to do this for simplicity, I think. So I need to provide some tree with which has no these duplicates here. That I need this because I can split correctly by the median my list. Okay, let's do this. For example, it's if I provide here 6, so I have unique elements at every position: 1 2 6 3 5 1. I'm sorry, 1 2 6 3 5, for example 11 and 22. Okay, and do this also for the second component: 1 2 3 4 6 8 7. I think okay. Okay, let's look at this case. They have, as you can see, the correct KD tree, because here we have 22 from the right and 2 from the left. So this 2 is less than 5 and 22 is greater than 5. Here we have 8, which is greater than 7, and 3, which is less than 7, and here they have 4, which is greater than 2, so and so on. They have balanced KD tree, and we can use this balanced KD tree to do the range search, actually a pretty fast range search. And let's look how can they do this. So how we do? Here they have this implementation. I do this. And what we have some query, some binary tree, and we produce a list which actually satisfy a list of containers, KD items, which satisfy to our query. Okay, and how do the range searching? So actually the check that, of course, if we have empty tree, we have empty list of results, and if they have node e with element e and left and right some branches, and we have some k dimension. So we have in the three cases here. If our element e inside our query, then we put this element into our solution. And also we need to go to the left and go to the right to check their other solutions. So actually go function produce to us the list of solutions here. So in the end, we go to the left and go to the right. But if we less than if we from the left of this interval, this say to us that there is no elements in the left part of that from the left part of this in this dimension, and we need to go to the right. Okay, because as you can see, for example, in this tree we have all the from the left we have all the elements which by the first component is less than 5, and here we have all the components which are greater than 5. This is how we define our KD tree and how we build it. Okay, and that was a range search. Of course, we can check that this thing works. For example, let's reload this thing. Let's build this tree tx. Let's print it. This tx3, sorry, and let's do the range search for this tree tx, and we need to provide some query here. I can use, for example, this query, and here I need to provide the intervals. And what are the intervals? For example, what if I want to, as the first component, use elements from 2 to 5, and as the second from 4 to 6. Okay, 4 to 6. And you can see I have the result. I have 5 and 6 because it is in my interval, and I have 3 and 4. 3 goes to this interval, 4 into this interval. Okay, but we haven't this 2 and 2 because this 2 is not in this second interval, and yes, so we can see that this range function works, and it works pretty fast. But of course, we have some constraint here in this tree. We have only unique elements at every dimension, but this can be fixed. Actually, I do the video about how can we handle the duplicate elements in a binary tree, in a simple binary tree, something like this. They can use here, I think. And what next? Also, I do some tail recursive implementation here. Here we have no tail recursion in this expression, and I do a little bit modifications to do the tail recursive range search in a KD tree. Let's write this range search in a KD tree. Tail recursive range search in a KD tree. Okay. Okay, I think that's all for today. Thank you for watching. Push like, push subscribe, and write comments. See you in the next video. Bye bye.